Hey, good morning, everyone. We'll get started. If you just send me a text in the chat, I will check that later for attendance. Okay. So let's get started. Let me share with you guys my screen here. All right. So again, a couple reminders here. Homework night is due tonight. Okay, at midnight. And then right after midnight, you should see the solutions to homework 9. Okay, I already put it up. I set it that to be available after the homework's due. And then exam 3 will be on Wednesday. Okay, so we are doing similar to what we did last time. So I will send you guys different versions of exam 3 in email. I will include in the email link. You can go there and download your exam. Okay, your individual exam. But the way of turning it back, I set it up a little bit differently. Okay, so if you go to the Moodle page, all right, you are going to see. So you see like the files and assignments solutions are here. You want to click on more here. All right, so I've set up exam 3 at the bottom over here. All right, so I'm not sure if you guys see the same screen page here as I do, but you might have a little bit different screen here. I switched to student view, so we might have just the same view. Okay, so on your exam 3, after you finish your exam, you want to turn your answers and worksheets here. So add submission over here. Okay, so I was sending out the exam about 9:10 on Wednesday morning in the email. Okay, and then you guys are going to work on the exam 3. You have until 11:20 to turn it in. Okay, so I would suggest you started turning in probably at latest like 11:15. Okay, so it takes a while to upload your sheets over here. Okay, any questions you guys have on exam 3? Just let me know. Okay, unmute yourself and let me know, or you can send me text in the chat. Okay. All right, so that's on exam 3. Let's get back to the lecture here of the day. All right, so kind of switch back to chapter 16. We are going to check on waves. So we have talked about wave in the last lecture a little bit on EM waves. Okay, so basically you can describe wave either as a sine function or cosine function. Okay, but that's on EMF waves. So in this chapter and then the next chapter, chapter 16, we'll talk about also part of it will be related to waves. Okay, so here we are mainly focused on talking about mechanical waves here. All right, so let's take a look here. So we are dealing waves every day. Okay, so if you go to a like say pond or a lake or whatever, you throw in a stone, so then there will be water wave generated. Okay, and then as we are using cell phones every day, we get EMF waves. Okay, also like there's other types of waves. So gravitational waves, as two black holes merges, we actually create a huge like gravitational waves. Okay, so then on the Earth here, we will be able to detect the waves of these two black holes merging. Okay, like quite a long time later, because it takes quite some time to reach the Earth. Okay. So basically in physics, wave is being defined as a disturbance that propagates or moves from the place it was created. Okay, so the most common ones we can see is the water wave. Okay, if you generate a water wave, you can see it will propagate outward from the where it's generated. Okay, now other wave we are dealing with each day, like sound wave, we can hear it, and then the EM wave, we are actually using it. Okay. Yeah, gravitational waves are not so easy to detect or to see, right? Now, the focus here will be on mechanical waves. So let's look at a couple examples, okay? So say if you are going out surfing, okay, then if there's a water wave hits you, then you kind of go up and down, okay, as the wave passes through you. Also, if you go to a larger sporting events, okay, a lot of people likes to do this, like doing waves, okay. So then there's a wave created by the crowd here. So actually, you are kind of like stand up and then create a wave, and then the person next to you will stand up a moment later. Okay, so in that case, we also create the audience creates a wave. Okay, now the question is, do you actually travel along the wave in these two examples in the direction of the wave propagation? Okay, so say wave goes from right to left, do you go from right to left or not? So the answer is no. Okay, you just move up and down perpendicular to the direction of the wave. Okay, so in this case you don't. All right. So again, going back to the water wave, if you see a seagull sitting on the water, and then if this wave hits the seagull, you'll see that the seagull will go up and down. Okay, and then the wave will propagate from left to right, say that way. Okay, as the figure shows here. So as we know, wave, we can describe wave either as a function or cosine function. Then this is like repetition events. Okay, so then for the distance that the wave repeats itself, okay, so if it propagates from left to right, so the distance it takes to repeat itself, say the maximum here travels certain distance later here, over here. So then this is called wavelength, all right? And then there's this, the time it takes from peak to peak is called the period, T, capital T, all right? And then how often does this happen in say, unit time, say 1 second, that's called frequency. So frequency is 1 over T. We kind of learned this earlier when we talk about the oscillation motions, okay? But just this is kind of just a review, okay? So then for the velocity of wave, it should be equal to the distance traveled in the one time period divided by one time period. So lambda over T will give you the velocity of the wave or the speed of wave. Or you can express in terms of frequency times lambda, okay? So either way. And then there's this equilibrium dashed line over here, and then there's this x and minus x, okay? So the x refers to the magnitude, okay? So the maximum displacement of the media from the equilibrium position, okay? That's the amplitude. And then sometimes we also use a as amplitude. I think more often we are using a as amplitude, okay, instead of x. For the sound wave, okay, so the fact you can hear the sound if we are in the classroom, you can hear me talking. It's because sound is a wave, it propagates through air, okay? So sound wave is very common, and then it has a speed of about 343 meters per second, or roughly 770 miles per hour, okay? At room temperature about 20 degrees Celsius, all right? So that might be the constant we will be using often, okay? So if you can remember, that's great, okay? All right, now for mechanical waves, there are basically two types of mechanical waves. Okay? One is called transverse wave, and the other is called longitudinal waves, okay? So for a transverse wave, it travels through media, okay? So say this wave in the slinky here, it goes from left to right, okay? But the media, the slinky itself, okay, it doesn't travel in the same direction as the waves, but perpendicular to the wave, okay? So the media travels up and down at any location, okay? So they are the movement of this media and then the wave, they're perpendicular to each other. So then this type of wave is called transverse wave, okay? On the other hand, if you generate a wave like this in the slinky, then the wave goes in the horizontal direction. The media, the slinky, moves back and forth, also in the horizontal direction, okay? So then this types of wave is called longitudinal waves, okay? Now for water waves or the wave people create, the audience creates in a sporting event, they are both transverse wave because the media doesn't travel in the same direction as the wave, right? On the other hand, the sound wave, okay, if you trace the, so sound wave actually propagates in air. So if you trace the air movement and the molecular movement in, if the sound wave goes through it, you'll see that sound wave goes in one direction, and the molecular also goes, air molecules goes back and forth in the same direction. Okay, so sound wave is a longitudinal wave. Okay. All right. Now, if some of you guys probably maybe playing guitar, electric guitar, so then as the guitar, as you plug the strings on the guitar, so the string will go back and forth, okay? And as the signal is picked up, okay, and then being amplified by a speaker here, then there's sound wave coming out of speaker. So this is a transverse wave on the guitar string, but the sound wave comes as a longitudinal wave. Okay, so the daily phenomenon could be complicated, could be a combination of both cases, right? All right. Now let's on the two major part or two types of the mechanical waves. Okay, longitudinal wave and the transverse wave. Okay. Now very often you will have interference of two waves. So for example, say if you throw one stone into a pond and then moments later you throw a second one nearby. Okay, so then you actually generate two waves. Okay, so then these two will meet each other at different locations, and then they will interact with each other. Okay, so we call that as wave interference. So when the two waves meets, all right, so the displacement of the media can be described with either sine function or cosine function. Okay, so then you have algebraic expression of the wave. If the two waves meets, you can actually just simply doing the algebraic sum of the two wave functions. Okay, so for example, if you have wave one, we can describe it as a function of y1 equals to whatever, like say x, function of x. Okay, and then y2, wave 2 is a function of x as well, but different, might be the same. So when the two meets, you simply add the two up. Okay, so the resultant wave will be equal to the algebra sum of wave 1 plus wave 2. All right. So if you have two identical ones, all right, so say in the figure over here, wave 1 and wave 2, they are the same. You can see the plus over here. So then they will add up. Okay. On the other hand, if the two waves are slightly different from each other, or actually this is quite different. It's so this guy, when they have maximum over here, the other one actually have minimum. Okay, so then when the two meet at the same location, you do y1, this guy, wave 1 plus y2, this guy. So then they will add up to be 0. So then this is destructive interference. Okay, so the two adds up to be 0. Right, the magnitudes. All right. In general, you don't always get identical waves, or you don't always get the exactly opposite waves. So then, in general, you may be having wave 1 like this, you have wave 2 like this. Okay, so the two add up, they become something like this. The resultant becomes something like this. So basically, this guy plus that guy. Okay. All right. Now, when the two, if the two waves, they are propagating in different directions, say one travel to the left, one travel to the right, and then they meet in the middle. Okay, so at the moment that they meet, they add up. All right, and then after they meet, they just pass by each other, just like nothing happened. Okay, so then they will just propagate as they initially. Okay, so it goes in that way for the second wave, and it goes to the left for the first wave. Okay. That magnitude wouldn't change. Okay, so that's one features of the wave. Okay, all the features of the wave. So after they meet, they just behave like never happened. Okay, so on that one. Now, what we have been looking at is they are purely just one-dimensional waves. Now, for two-dimensional waves, so it happens the same. Okay, you just describe the wave differently, but in two-dimensional. Okay, so now if the two-dimensional wave meet, and different locations, okay, so there should be also interference. So at some point, if the peak meets the peak of the two waves, then they will add up, become constructive interference, okay. And then if the peak meets the valley of the other wave, then that's destructive interference. Okay, so here where the destructive interference happens, here is where the interference, constructive interference happens. Okay. All right. Now, if you have waves coming from two locations or from two sources, okay, so then what happens here? So, for example, if you have two speakers, they give out two identical waves, sound waves. Okay, so they start starting with maximum, okay, at the same time, and then they will have minimum at the same time. Okay, so if that happens, the two are identical waves just coming from two sources. We call the two sources to be in phase. Okay, so they are synchronized. Whenever they are given, they give out the same the peak for the wave. Okay, then the other one would also have peak. Okay, so that happens. So then at different locations, when the two waves coming out of these two sources meet, okay, so at point A, B, C, different locations, they kind of add up differently. Okay, if they travel the same path to reach, say, point A, if point A is at the middle of two sources, then they travel the same path, then the maximum will meet from one wave will meet the maximum from the second wave, or the minimum from the first wave will meet the minimum of the second wave at point A. Okay, so when this happens at point A, you will see constructive interference from the two sources. All right. Now, at certain different locations other than point A, you might have, say, because the paths from the two sources, the waves coming out of two sources, they are different. Okay, so you might have when the maximum comes out of source one reaches point B, actually minimum from source two will come out and reaches point B. Okay, in that when that happens, then you have destructive interference. Okay, so it depends on location due to path differences of the waves coming out from different sources, you would have different types of interference. Okay, and then C might be another scenario. So because of also the path difference, you might well have the scenario like at point C when the maximum from the source A reaches point C, but at the same time you have maximum from source 2 reach point C. Okay, that might well be the case, or the other way around. Okay, so it just depends on the difference in path. Okay, now mathematically, if the two waves reach at certain location when they travel the same path, okay, so then the path difference is 0. All right, and then if the sources are in phase, so then they will be just constructed interference. Okay, now at other locations, if the path difference is multiples of the wavelengths, then you still get the constructed interference. Okay, so if it's differ by multiples of lambda, the wavelengths, then you actually get maximum. Okay, as well at the same locations from the two sources. Okay, at the same time. Now, the other stream is when the path difference are multiples of half waves. Okay, say the difference is 1/2 lambda, 3 halves lambda, 5 halves lambda, etc. Okay, so then when the maximum from source A reach point a particular point, then will be minimum from the other source reach at that point. Okay, so then the two will cancel out because you have maximum meeting the minimum will cancel out become 0. So then when that happens, you have destructive interference. Okay. Now, on the other hand, if the two sources are out of phase, okay, so basically that happens when source one, if at certain given moment, source one gives out, say, a peak intensity, then source two will give a minimum intensity. Okay, so they are actually in opposite phases. Okay, so they are different by in mathematically, if you use angle, then they are different by 180 degrees or pi. Okay, so if that happens, even though you have the same setup, so one source is out of phase compared to the other source. Okay, so then when they reach, say, if they travel the same path, reach at certain point P, they still will have now not constructive interference but destructive interference, because now one maximum from source 1 will meet the other minimum from source 2, so they will cancel out. Okay, that's because their sources are in opposite phases. Okay, so then it's the other way around. So if the path difference is half of lambda, say 1/2 lambda, 3/2 lambdas, 5/2 lambdas, etc., then you'll have this constructed interference. Okay, if the path difference is multiple of lambdas, then you get destructive interference. Okay, so you want to be careful about when you are solving a problem, if the two sources are in phase or they are out of phase or in the opposite phase. Okay, sometimes people say out of phase, that means probably they probably refer to opposite phase, but it's more accurate to say opposite phase, okay, than out of phase. Okay, because anything other than in phase is called out of phase. Okay. All right, so let's take a look on the first example of the day. Here it says two speakers. Okay, so these are two sound wave sources. They are out of phase. Okay, so that means whenever speaker 1 gives out maximum in intensity, then speaker 2 will give out wave in minimum in intensity. Okay, so it says that they are out of phase. They are 3.5 meters apart, both pointing towards a wall 5.0 meters in front of them. Okay, an observer standing against the wall midway between the speakers hears destructive interference. Okay, so if the observer is in the middle of the two sources, because then the two sources are out of phase, although the path difference is the same, but because the sources are out of phase, so he hears destructive interference. Okay, now as he moves to one side by 0.84 meters, then he hears the constructed interference for the first time. Okay, so that means at this moment, the paths from the two sources to the observer, they are actually differ by half lambda. Okay, so then it's asking what would be the frequency of the sound emitted by the speaker. Okay, so let's take a look on this one here. Okay. So let's take a look here. All right, I'm going to draw a picture over here. So there's this source 1 by speaker 1. All right, there's speaker 2 over here. They're out of phase. Now in the middle is where the observer hears the destructive interference. So R1 and R2 are the same over there. Now when he moves about 0.84 meters over here, so this is then the new location. Okay, so for wave 1 to reach at the observer's location, this is the R1, the path 1. Okay, and then for wave 2 from speaker 2 to reach the observer, this is path 2. Okay, R2. All right, this is 3.5 meters apart. This is 5 meters over there. So I'm going to just draw it over here. Say this is 5 meters. Okay. Okay. So they're out of phase. The two sources are out of phase. All right. So at this location, when the observer hears the construct interference, so that means the difference between R1 and R2, now it should be equal to half of lambda, because this is the first time he hears that. Okay. If it says the second time he hears the construct interference, then that means like 3 halves. Okay, so it's 1/2, 3 halves, 5 halves, etc. Okay. All right. So it also tells us this is sound wave. So sound wave have a speed of wave speed v equals to 343, or is this even 343 or 340? So yeah, 340. So a lot of times we just use 340, okay, as the speed of sound in air at room temperature. All right, now V should be also equal to frequency times lambda, okay? So you can see we are looking for frequency here. All right. So we are given V, we are looking for frequency here. So then we need to know lambda. Okay. Now lambda is related to the path difference over here in this equation. So let's see if we can figure out lambda from here. Okay. So R1 here. All right. R1 is if you look at the geometry here, so R1 is this hypotenuse of this right angle triangle. Okay. This is phi. This is, so he moves by 0.84 meters. Okay, so this is 0.84. This is exactly half of the 3.5. Okay, so then you can figure out R1. R1 should be equal to square root of A squared plus B squared. So A is half of 3.5 plus 0.84. A squared plus B squared will be 5 squared. Okay, this is R1. R2 will be, so minus R2, square root of, so this is half of 3.5. You should subtract that by 0.84 to get this length, okay? So that's purely again from geometry. All right, so square, and then this R2 is hypotenuse of this right angle triangle then, okay? So plus 5 square, okay? Equals to half lambda. So you can see here then you can solve for the lambda, okay? From there. So if you plug in the numbers of here, so then you get left hand side, okay? And then multiply by 2 will give you lambda, okay? So if you do the left hand side, if you plugging them into the calculators, it's 0.549 meters, okay? So lambda will be equal to twice of that. So then lambda equals to 2 times of 0.459 meters, which is 1.098 meters. Okay, now we have this lambda, then we can put that into the expression over there. So the frequency should be equal to velocity divided by lambda. Okay, velocity is 348 meters per second divided by the lambda, 1.098 meters. Okay, so this will give you the frequency. It's about 309.7 hertz, okay, or roughly 3.10 times 10 to the second hertz, okay, so either way. Okay. All right, let me know if you have any questions. You can unmute yourself and speak up, or you can send me text in the chat. Okay, so if you guys don't have questions, then we'll move on here. All right, so now let's look at the mathematically when the two waves interfere. Okay, so as I said, you simply just do the algebra sum of the two. Okay, so for example, if you have wave one, if you express in a sine function, so let's say this is the amplitude of the wave one, and sine of kx. Okay, now if you have a second wave that is also the same amplitude, sine of kx plus, okay, a difference, okay, in phase. Okay, so this is that means they have different in phase. Okay, so in trigonometry, if you have a sine function, if they are differ by a little bit different, and we call it that's different in phase. Okay, so so this is what happens also in a general cases when you have two waves they meet. Okay, they do not necessarily have to be in the same phase or exactly opposite phase. Okay, so a lot of times they are differ by just a random number of phase. Okay, so then we can use that. We can say that. Okay, so then you can express them in these two expressions. So y1 will be wave 1, y2 will be wave 2. They are different by any given number of difference in phases. Okay, so then you'll be doing algebra sum of the two. Okay, so y1 plus y2. I think I don't have exactly full expression. So a lot of times when we wave, it should be as a function of position x, and then it should be also a function of omega, or the function of time t. Okay, so in this case, I should have written it out in full expression. So this is y1 as function of x, also as function of time t, and then this is y2 as function of x, as function of time t, and then differ from y1 by a factor of that. Okay, so mathematically, if you add the two up, okay, so sine, if you call this as theta 1, this as theta 2, okay, so then sine theta 1 plus sine theta 2 should be, okay, this is a trigonometry identity. If you are not familiar with them at this moment, you can review later. Okay, but basically, these two, if you add them up, it should be twice cosine of the two angles difference divided by 2, times sine of the sum of the two angles divided by 2. Okay. So this is theta 1, this is theta 2. If you do theta 1 minus theta 2, then this becomes just minus theta. Okay. And then on this one, you get twice of this, twice of that. Okay, so we'll see. So the resultant wave will be twice of a cosine of theta divided by 2. Okay, and then sine of, so this is half of theta 1 minus theta 2. This is half of theta 1 plus theta 2. Okay, so you can see that if theta is very small, okay, if the difference is very small, then to the extreme that theta is equal to 0, then we have the constructed interference. Okay, so that means they are in phase. The phase is the same. There's no difference in phase. Okay. So when that happens, then you have constructed interference. So with wave 1 and wave 2 are exactly the same, so they will add up. Okay. Now the other extreme is if theta is equal to 180 degrees, okay, or out of phase, or the opposite phase. Okay. So then when the wave 1 have maximum, wave 2 will have minimum. Okay, so then the two will cancel out totally. Excuse me. So this is called the destructive interference. Okay. All right. Now let's take a look on the second example of the day here. Okay, so this one says two waves with same frequency, wavelength, and amplitude are traveling in the same direction. If they differ in phase by 90 degrees, okay, so that little delta is equal to 90 degrees, and each has an amplitude of 4. So A is equal to 4. What's the amplitude of the resultant wave? Okay, so then we'll be just using what we had from the previous slide. Okay, we are going to say y1 plus y2. All right, so y1 plus y2, okay, is equal to 2a cosine delta divided by 2. Okay, this is the amplitude sine of whatever kx minus omega t plus delta over 2. Okay. Now we are just focusing on the amplitude, so this is the new amplitude, and this is the new amplitude term. Okay. So it says if delta is equal to 90 degrees, okay, then A is equal to, original A is equal to 4.00 centimeter. What will be the new A prime, okay, of this guy? Okay, so A prime is equal to 2 times A cosine of delta over 2. Okay, this is 2 times 4.00 centimeter cosine if the delta is equal to 90. Okay, so 90 degrees, then it's 40 degrees, 45 degrees. Then you can plug the numbers into your calculator. It's going to be 5.66, okay, centimeter. That will be the new amplitude. Okay. So when the two add up, okay, if they are the same, if they have the same wavelength, okay. So actually, let me just go back to the original expression here. So K, it's actually related to the wavelength, okay? K is actually equal to 2 pi over lambda. It's called wave number, but it's related to wavelength, okay? And then omega is related to frequency. Omega is equal to 2 pi over frequency, okay? So yeah, omega is called angular frequency. This is called wave number. Wave number, okay? And then this is angular frequency. It's related to frequency, okay, in that fashion. All right. So in case you were wondering what are K and omegas, okay. So K is the wave number is equal to 2 pi divided by length. Omega's angular frequency is 2 pi. Actually, I think omega is 2 pi times frequency. 2 pi times frequency. Okay. All right. So, okay, anyway, so then this is your new amplitude here if the phase difference is 90 degrees. Okay. Now, also, this is part A. For part B, it's asking you now only in the other scenario, if A prime, the new amplitude is given also as 4.0 centimeter, then what will be the delta? Okay. What will be this delta differences, the phase difference? So then you're again looking at this expression, okay? But you'll be just solving for delta instead of A prime, okay? Because A prime this time is given, so you're looking at this guy again, all right? But you're solving for this guy. So then what you are doing is you'll be divide both sides, or you can just put it in the numbers here. A prime is 4 centimeters equal to 2 times 4.0 centimeter cosine of delta over 2, and then you're looking for delta, okay? So you can see 4 and 4 will cancel out. So then 2 here, 2 times this guy equals to 1, so that means cosine of that equals to 1/2, okay? Cosine of delta 2 over 2 equals to 1/2. Now, because you have cosine here, you want to do inverse of cosine, okay? So you do inverse of cosine to the right-hand side here. To get rid of cosine, you'll be doing also inverse of cosine to the left-hand side, okay? Inverse of cosine 1/2 tell you that equal to 60 degrees if you plug in that into the calculator, okay? So then that equals to delta divided by 2, all right? So then you multiply both sides by 2 to solve for your delta. Delta is 120 degrees in this case, okay? All right. Any questions you guys might have on this one? Okay. So if not, okay, we'll move on here. Okay. Now, the next we'll be looking at standing waves. Okay. So we have done this lab previously, but basically for standing wave, it's the wave confined in. So if you have a stream, then it's confined in the stream. Okay. If you have an air column, then it's wave confined in the air column. Okay. So it's a wave being confined at the media. Okay. So that means a standing wave is a fixed. It's fixed in location, okay, and then they oscillate in time. Okay, so if you have guitar string, if you plug it, it will vibrate up and down, generating a standing wave in the string. Okay. Now you might have a standing wave like this. Okay, you might have a standing wave like that, and then in the video demo you guys watched earlier, you will have like a few different numbers of loops in the string. Okay, so you could have different scenarios there in the fixed string. Okay. All right. So the first scenario you will have is something like this. If you have a string fixed at two locations, okay, then it can vibrate up and down like this. So where the string vibrate most, okay, so that means maximum amplitude here. It's called um, actually let me take this from this here, where the vibration is minimum or it doesn't vibrate at all. That location is called the nodes, okay. And then where the vibration is most is called antinodes. Okay, so that's antinode, that's nodes here. So this is the first one. If you have a wave, standing wave like this in a string, this is the first harmonic, okay, of it. And then it's called the also called the fundamental wave there. Okay, now you can have other scenario like this. The second one you can have is you have nodes at the two ends, then there's additional nodes at in between. Okay, and then there are two antinodes over here and there. Okay, so then this is called the second harmonic. Okay, so when the two ends are fixed, then at the two ends you have nodes. Okay, and then you might have additional nodes in between. Okay, so the first scenario is the two ends. You have nodes at the two ends. There's no additional nodes, so it's the first harmonic. And then when you have one additional nodes in between, it's called second harmonic. When you have two additional nodes in between the two ends, then you have third harmonic, etc. Okay, so that's how you distinguish them from one another. All right. So if you have a standing wave in a fixed string on both ends, okay, so then for different harmonics, their frequencies can be determined, okay, by looking at the frequency. If you do the equation of frequency equals to wave divided by, or the velocity of the wave divided by wavelength, okay. So the first harmonic you have like two nodes and one antinode. So that is actually half of one wavelength, okay? So then the length of the string will be one half of the wavelength, okay? So then wavelength should be twice of the length, L, okay? So lambda should be equal to twice L. So then the first harmonic will be V equals to 2L, or V divided by 2L for the frequency, okay? And then the first harmonic should have a wavelength of 2 times L, okay? For the second one, third one, etc., actually can be expressed by this equation. Okay, so the first harmonic is having frequency of that guy, so the second harmonic is 2 times of that, and the third one is 3 times of that, etc. Okay, and then the wavelength is the other way around, is lambda divided by n, lambda 1 divided by n. Okay, so this is when you have two ends of the string being fixed. Okay, and then this is similar if you have a xylophone. Okay, so a xylophone device, both of them like xylophone very much. Okay, so then you will have standing waves in this. So because the xylophones have different lenses here on different bars, so they will produce different frequency. Okay, then you hear different tones on the xylophone. Okay. All right. So in summary, this is what you get when the string has two ends fixed, or on xylophone cases, the metals have two ends fixed. So then you will have a standing wave in the metals. Okay. So first harmonic, you will have n equals to 1, lambda 5, and then frequency is V divided by L. Okay. Okay. All right. And then the second one, this is what you have. Okay, so if you are solving for a problem for a string with two ends fixed, you'll be looking at this summary figure here, or you can refer to the equations in the previous slide. Okay. All right. So let's see. So let's take a look on the third example of the day. Okay. So this one is standing wave. So this one says a wave traveling on a slinky that is stretched to 4.0 meters, which takes 2.4 seconds to travel the length of slinky back and back again. Okay, slinky and back again. So travel back and forth. Okay, takes that much of time. All right. So what's the speed of the wave? All right, so we can see for the speed of wave, there's several different ways of calculating it. Okay, you can do frequency times the wavelength. Okay, in this case, you are not given frequency, you are not given um, wavelength. All right, so now we'll just have to rely on the other knowledge we learned before. Okay, so in this case, it actually gives you the distance and then it gives you the time. Okay, so we can use the what we learned in kinematics. So velocity should be equal to distance divided by time t. Okay, so the wave travels linearly back and forth, takes 2.4 seconds. So then we can use that piece of information to solve for this. Okay. Now keep in mind the slinky has length of 4 meters. Okay, but it travels back and forth, so twice on that. Okay, divided by the time it takes 2.4 seconds. All right. So then that gives us 3.33 meters per second, okay, as the speed of the wave. All right. So this is part A. Part B says using the same slinky stretch to the same length. Okay, a standing wave is created which consists of 3 antinodes and 4 nodes. What frequency must the slinky be oscillating? Okay, so in this case, the slinky is stretched again with the 4.0 meters. Okay, now it says it has 3 antinodes and 4 nodes. Okay, so you can stretch, so 4 nodes, one at one end, the other one at the other end. So that means there are 2 additional nodes in between. Okay, so you can draw it like that. So nodes, nodes here, antinodes, antinodes, antinodes. Okay, 4 nodes, 3 antinodes. Okay, so you can see if this is a scenario, so this is 4.0 meters for the length of it, then the wavelength, this should be one wavelength. Okay, so this should be lambda. Okay, so from the figure here, you can see your lambda is going to be 2/3 of L, right? So now you have your lambda. Okay, you're looking for what here? You're looking for frequency here. Okay, so now you can, for frequency, the one we did earlier, for the first example, we use velocity equal to frequency times lambda. So we can use that one, okay, again here. Because velocity, we have it in part A. Now it says if the slinky is stretched to the same length, and then, so if that's the case, then you will have the same velocity, okay? Because this is a standing wave in a stream. In the slinky case, now although we haven't learned this, but in the lab we learned that velocity is equal to square root of t over mu, right? So this is a mass density, this is t tension in the slinky. So if it's being stretched to the same length, that means t is the same. So this really should be the same, okay? Thanks to the knowledge we learned in the lab, okay? So all right, so then this is what we have here. So then we can calculate this. The frequency should be equal to velocity divided by lambda, okay, where lambda is that guy, so 3.33 meters per second divided by 2/3 of L, okay. So you want to plug in all these numbers in your calculator. Then it's going to tell you this is 1.25. So this is 1.25 hertz. Okay, that's the frequency there. Okay. All right. Any questions you guys might have on this one here? Okay, so if not, then we will move on. Okay, so this is what we did in the lab. In the lab, we have, actually we pretended to do in the lab. In the lab, we would have a vibrator here, gives our sine function, then we will have a mass attached to it, okay? Then we can, by changing the mass, we have different tension in the stream that will create different speed of the string over there. Okay? And then you can have different loops. Okay, so that's what we pretended to do in the lab anyway. All right. Now we have checked when the string has both end fixed. Okay, so what if the string just has one end being fixed? Okay, so if this is the case, so this end is fixed and then this end is loose. Okay, it can move up and down on a rod like this. Okay, so then what happens is if you create a wave on the string over here, so this is fixed. Okay, by the vibrator here, then there's this node here. Okay, now the other end will become anti-node, okay, because you will move the most, okay, vibrate from the equilibrium position the most, okay. So then you'll have a node, an anti-node, okay. So this is the first scenario you can have for the standing wave in the string, okay. So in this case, then the wavelengths, you can see if you can extend this back forward here, you can see the whole picture for flow wavelengths. Okay, and then you can see this is only one quarter of it. Okay, so then lambda will be equal to 4 times of the length. Okay, and then for more cases, if you have different velocities of the waves, then you will have like two. Now you will have one additional nodes in between, in the middle somewhere, and then the other end is still anti-node. Okay, so the unfixed, the free end is always going to be the anti-node. The fixed end is always going to be the nodes. Okay, so then you will have additional one node in between. So then you will have one anti-node. Okay, two anti-nodes, two nodes. Okay, then this is 3/4 of the wavelength. Okay, so the wavelength on the second scenario will be 4/3 times L. The third one will be 4/5L, okay, etc. like that. Okay, so then in that case, you can summarize the scenarios here. You can see the length is going to be equal to n divided by 4. Okay, of the frequency of the wavelength. Okay, so the first one is 1/4 of the wavelength equal to length. Okay, then the second one will be 3. So n here is the odd numbers 1, 3, 5, 7, etc. Okay, so then the frequency will be velocity divided by lambda. Okay, in this expression over here, so it's equal to n times f1. All right. So fundamental frequency is that guy. So you can see in this case, it's also n times the fundamental for the frequency of nth harmonic. Okay. So, but in this case, n is equal to 135. Okay. In the previous case, n is equal to just integer numbers. Okay. So this is the second scenario when you have the other end of the string is being free to move. Okay. All right. So let me see. I think I'm going to stop over here. Okay, so then we'll come back next time. The standing waves are in air columns. Okay, so if you have air columns, you can also produce standing wave in air column, but we'll save this for later. Okay, so we'll stop here today. Okay, remember on Wednesday when we come back, we'll have our exam number 3. So actually we don't meet online, but I will send you guys exam in the email. You can download it and then work out on that. Okay, and then turn in your answers and results and the worksheets on Moodle. Okay, that will save me a lot of time because then I don't have to convert it into PDF and create it in PDF. Okay, so we'll stop here. Okay, see you guys actually after the break. Okay, so have a nice Easter break and then good luck on your exam and then we'll see you guys back. Okay, bye.